Metals. Most metals come from minerals. Minerals is a naturally occurring substance with a range of chemical composition. Mineral deposit concentrated enough to allow economical recovery of a desired metal is known as ore. The most abundant metals which exist as minerals in Earth's crust are aluminum, iron, calcium, magnesium, sodium, potassium, titanium, and manganese. Seawater is a rich source of some metal ions, including sodium, of course, magnesium, and calcium salt. Furthermore, vast areas of the ocean floor are covered with manganese nodules, which are made up mostly of manganese, along with iron, nickel, copper, and cobalt in a chemically combined state. Because metals in very combined forms always have positive oxidation numbers, the production of a free metal is a reduction process. Preliminary operations may be necessary to convert the ore to a chemical state more suitable for reduction. How a pure metal is obtained by reduction form, its combined form depends on the standard reduction potential of the metal. Most major metallurgical processes now in use involve pyrometallurgy processes carried out at high temperatures. The reduction in these procedures may be accomplished either chemically or electrochemically. Let's talk about chemical reductions. We can use a more electropositive metal as a reducing agent to separate a less electropositive metal from its compound at high temperatures. On this slide, you can see some examples. For example, reduction of vanadium, titanium, chromium, manganese by using other metals. In some cases, even molecular hydrogen can be used as a reducing agent, as in the preparation of tungsten, used as filaments in light bulbs, from tungsten trioxide. Electrolytic reduction is suitable for very electropositive metals such as sodium, magnesium, and aluminum. The process is usually carried out on the anhydrous molten oxide or halide of the metal. This is a general process. The metallurgy of iron is the most important. Iron exists in Earth's crust in many different minerals, such as iron pyrite, siderite, hematite, and magnetite. Of these, hematite and magnetite are particularly suitable for the extraction of iron. The metallurgical processing of iron involves the chemical reduction of the minerals by carbon in the form of the coke in the blast furnace. The concentrated iron ore, limestone, and coke are introduced into the furnace from the top. A blast of hot air is forced up the furnace from the bottom, hence the name blast furnace. The oxygen gas reacts with carbon in the coke to form mostly carbon monoxide and some carbon dioxide. These reactions are highly exothermic, and as the hot carbon monoxide and carbon dioxide gases rise, they react with the iron oxides in different temperature zones. The key steps in the extraction of iron you can see in this slide. Limestone decomposes in the furnace to calcium oxide and carbon dioxide. The calcium oxide then reacts with the impurities of the iron, which are mostly silicon dioxide or sand and aluminum oxide. The mixture of calcium silicate and calcium aluminate that remains molten at the furnace temperature is known as slag. By the time the ore works its way down to the bottom of the furnace, most of it has already been reduced to iron. The parent temperature of the lower part of the furnace is above the melting point of impure iron, and so the molten iron at the lower levels can be run off to a receiver. The slag, because it is less dense, forms the top layer above the molten iron and can be run off at that level. Iron extracted in this way contains many impurities, and it called pig iron. It may contain up to 5% carbon and some silicon, phosphorus, manganese, and sulfur. Some of these impurities stem from the silicate and phosphate minerals, while carbon and sulfur come from coke. Pig iron is granular and brittle. It has a relatively low melting point, about 1180 degrees, so it can be cast in various forms. For this reason, it is also called cast iron. Metals prepared by reduction usually need further treatment to remove impurities. The extent of purification, of course, depends on how the metal will be used. Three common purification procedures are distillation, electrolysis, and zone refining. Metals that have low boiling points, such as mercury, magnesium, and zinc, can be separated from other metals by fraction distillation. One well-known method of fraction distillation is the Mond process for the purification of nickel. Carbon monoxide gas is passed over impure nickel metal at above 70 degrees to form the volatile tetracarbonyl nickel with boiling point 43 degrees. A highly toxic substance which is separated from the less volatile impurities by distillation. Pure metallic nickel is recovered from this tetracarbonyl nickel by heating the gas at 200 degrees. The carbon monoxide that is released is recycled back into the process. Electrolysis is another important purification technique. The copper metal obtained by roasting copper sulfide usually contains impurities such as zinc, iron, silver, and gold. The more electropositive metals are removed by an electrolysis process in which the pure copper acts as the anode and pure copper acts as the cathode in a sulfuric acid solution containing copper 2 plus ions. Reactive metals in the copper anode, such as iron and zinc, are also oxidized in the anode and enter the solution as iron 2 plus and zinc 2 plus ions. They are not reduced at the cathode, however. The less electropositive metals, such as gold and silver, are not oxidized at the anode. Eventually, as the copper anode dissolves, these metals fall to the bottom of the cell. Thus, the net result of this electrolysis process is the transfer of copper from the anode to the cathode. Copper prepared this way has a purity greater than 99.5%. Another often used method of obtaining extremely pure metals is zone referring. In this process, a metal rod containing a few impurities is drawn through an electrical heating coil that melts the metal. Most impurities dissolve in the molten metal. As the metal rod emerges from the heating coil, it cools and the pure metal crystallizes, leaving the impurities in the molten metal portion that is still in the heating coil. Then the molten zone carrying to the impurities, now at increased concentrations, reaches the end of the rod. It's allowed to cool and it then cut off. Repeating this procedure a number of times results in metal with a purity greater than 99.99%. Metals are lustrous in appearance, solid at room temperature, with the exception of mercury. Good conductors of heat and electricity, malleable. The electronegativity of elements increases from left to right across a period and from bottom to top in a group. The metallic character of metals increases in just the opposite directions. That is, from right to left across a period and from top to bottom in a group. Because metals generally have low electronegativities, they tend to form cations and almost always have positive oxidation numbers in rare compounds. However, beryllium and magnesium in group 2A and metals in group 3A and beyond also form covalent compounds.